Right. Yes. Okay. So it's supposed to be the second part. So I jump into page 22. So let me say the one of the thing that the previous theorem from all the way to BDF theorem, they successful to describe the extensions is because the Kroner algebra, the Huaxin algebra in that case, is simple. So look at the, so the B is still the same B. By a result of George, you have a unique idea, a proper idea. So instead of so I'm not going to continue a construction, maybe just a draw or something. So you have an idea. This idea contained B. So you have another quotient. Let me write this way. So if you look, let's say D is the disk, unit disk, and you look at the continuous functions on the unit disk, and you look at the Both-Bay invariant of extension. And of course, there's a disk, so it's homotopy to one point. And you will think that the extension is just trivial. But then the example I was trying to show you is that you look at this map. So you can construct a map that one is this still injective. So there's a phi 1 bar, and they are still injective. But then you can also produce another map phi 2, but then this map is not injective. Actually more than that, but it's not injective. Then they cannot be approximate unitary equivalent even in this level, since they have same spectrum in this quotient. Even though if you compute the KK theory, and won't tell you much since this is just a D. So, so I'm not going to show the whole example, but let's just tell you that you don't really in general get this. So what I was trying to do is to construct actually two of those. And so let me go to, these are the examples that I try to construct. But the question's still there, how to classify these essential extensions of this form. And there actually has another question, is if you have two trivial extensions, say you already lifted, are they actually equivalent? Do you have the Voiculescu theorem? So I can build example shows that's also in general not true. Okay. So say you have two maps from A to the multiple algebra. And when this unitary, this approximate equivalence holds. Okay. In the classic case, yes, it is. But you can produce examples, they are not in this case. So let me move. So this is also try to give an example, but let me just passing that. So you sort of believe me this from this picture, because there is extra quotient. They are not necessarily be the same. Okay, so now let's look at a weak condition equivalence. So you say you have two essential extensions. We say they are approximately unitary equivalent if there exists a sequence of unitaries such that this holds, without saying the other difference. So the previous one we also insisted the difference of the unit equivalent, well, I should say they are equivalent in the quotient. Okay. But let's ignore that. And you can still think of this equivalence relation. So the A unit of C-star algebra, let's temporarily use this notation for the approximately equivalent, unitary equivalent extensions of A by B. Then you can compute, say, if B is a non-unitary but sigma unitary simple C-star algebra with a continuous scale. A is a unitary separable amenable C-star algebra which satisfies the UCT. So this is unitary extensions, and you can compute this is actually, you can use a KL to determine the approximate unitary equivalence class of unitary extensions by computing the KL from A to the Kroner algebra. Okay. But it's much weaker than the previous one because we don't know the difference is actually compact or differences in the ideal. Only approximate unitary equivalence class. And then you can say something is approximately trivial. Well, you just have a limit of trivial ones, okay, or approximately trivial. And then you can have a statement like this. Now, by the way, I should have mentioned that with this condition, then this phenomenon won't happen. And the Kroner algebra is actually simple. So we want to know when is approximately trivial. It says that K1 has to be 0, and image of K0 must be there, otherwise cannot lift it to the affine function maps. And everything else you want to be 0. Okay, so look at the KL, these are 0. So I'm not going to explain these groups, but just say this could be done in a way. If you insist you want to know what are the approximately trivial ones. You can say a little bit better. In the case the commutative, then these are actually if and only if these are approximately trivial. But that is expected that now you look at the KK or KL not as a original one, but we look at the KK of C of X to the Kroner algebra. Okay, so that's what is expected to have.
Question.
Oh, so so we talk about this question. Okay, here's a question. So how many of such maps and how to classify them? So we give example that things on this level are the same, but on the quotient are different, so that you must use something else. I will say, yes, we can by looking at different KK element. Right. So in the first kind of result is instead of looking unitary equivalence, we look at approximately unitary equivalence. Instead of looking the trivial extension or splitting extension, we look approximately splitting extensions. So in the community case, you can have a better statement to say, and only if. Okay. One can do a little bit better. Now, let's look this a special case. We say you have a class of amenable separable Z-stable C-star algebra. These are also stably projectionless simple C-star algebra with a unique tracial state and satisfy UCT. Now, if B is in this class, then B never unital, since there is no projection whatsoever, and actually, let me put this way: that in the J, I also want the kernel of this to be the whole K theory. This is not a consequence, but the assumption. There are two distinct C-star algebra in this class. Namely, one is the Razak algebra, W, which has a trivial K theory. And there is another one we denote by Z0, which is a stably projectionless simple C-star algebra with a unique tracial state, such that K1 is 0 and K1 is Z, but it's the same as the kernel of the row. So it's vanishing. Two of these things. Let me point out one of the reasons is that the W will kill K theory, and you tensor with the Z0 as a group. You won't change the K theory or traces. Okay. So let's look at extensions of this form. Say W, E, and A. Now, why I want to do that? Well, you want to study non-simple C-star algebra. Maybe we put a small idea in the sense that the K theory is trivial. And you ask yourself, can we classify those extensions or classify all the C-star algebra with this form? This has a trivial K theory. And one first thing is, can we classify the extensions? Now, if you look at the KK theorem, then it's 0, because W has a 0 K theory. So KK, in the usual way you look at KK theory, there's nothing there, 0. But very quickly you realize there are lots of extensions of these form, and they are not isomorphic. So one step of time. So let's look at this kind of extensions. So you convince yourself that you look at a KK element, then it's just 0. But so consider the essential extensions of this form. B is one of those. In particular, the case B is the W, okay, the Razak algebra. And you can define something as a strongly unitary equivalent if you can find the unitary on upstairs, so that they are equivalent in the downstairs. And let's temporarily use this notation for strongly unitary equivalence classes of essential extensions mentioned above.
So you answered my question about the non-community case. So the B is the compact operator. The B is not the compact.
Yeah, B now think about like Razak algebra. Okay. So let me mention a result with the pin. So assume A for now is embedded. It can be embedded into W. And so you look at two extensions, then they are strongly unitary equivalent if and only if the KK elements are the same, but this KK element, not the extra group. KK. So these things are isomorphic as a group. But you will ask what happens if B is W and it's actually not zero. Then you traditionally, when you look at the extension, you will ask when this short exact sequence is split. So we call it trivial extensions. And if it's trivial and a diagonal, I hope nobody asks me what a diagonal is. I'm not going to explain it. So if this thing is a zero as a KK element. Diagonal is really a diagonal. That means there is no projections in W, but you could have maps like this. Keep adding, right? These are orthogonal to each other. And you could have those things, and these called diagonal. And you can also define quasi-diagonals. And there are cases all quasi-diagonals are trivial and are unitary equivalent. If the K theory is just K0 is the same as the infinitesimal element, then all trivial extensions are unitary equivalent. So that's good news. And the zero element in KK give you trivial extensions, which is nice too. But if not, then there are essential trivial extensions which are not quasi-diagonal. And not all essential trivial extensions are unitary equivalent. So this is a very special case. And just say these things can be described still using KK theory, but just look at different KK theory. Okay, so I will move ahead. Now, if you tensor Z0, then you can change the K theory as a group. And then you for any simple C-star algebra, you tensor with Z0, then come to the class that I was talking about. And so in that case, we can have a slightly better statement that these can be described by the as expected. Okay. Now, let me try to say something somewhat complicated. I'm not sure that I want to say too much about a pairing, but let's say KK of A to M B is a home of K0 to R. Okay. And so why I want to introduce all these notations is we can say the following in this case. So the trivial, the map to this is 1-to-1 on that, and all the let me just go to this page. So it tells you what's trivial, well, which extension split, if and only if this map is living here. And tells you all the trivial extensions. So there are lots of them. Okay, and all these are trivial. And in this case, you can see that the zero element not necessarily corresponding to the trivial extensions, or there are something not zero still can be lifted. But so in fact, there are uncountably many different elements in N. So this trivial extensions does not even form a semi-group. for example, that if you have a KK element look like this, then tau is not splitting because I is too big. And there is no homomorphism on the up level that can be induced by lambda if I is too big. So this will. So, but in this case, this is just show you that in general it's not a semi-group.
But in general, there is also an addition.
No, say it again.
You also add.
You can add. Yes, it's a group. The extension itself is a group, but the trivial extension is not even semi-group. Unfortunately. So by UCT, we'll look at this. This is you have a short exact sequence. So therefore,
Are you saying the sum of two trivial extensions is not trivial anymore?
in that's right.
In what sense?
It depends how you view this the sum. So the sum is you add too big, you can, unless you stabilize it, you cannot get a trivial extension. You add down there by adding, you can always so there is the Kroner algebra is purely infinite. There are zero projections.
I mean, there may not be room for a complement.
That's right. So the add it come out. It's not. If you look carefully, you expect it to happen. But you first look, it's like, okay, so everything should be nice. Something are good, something are not.
I don't think it's surprising. If you
No, it's
add things and what's left over gets smaller.
That's it. Could it be smaller? Could it be big? So just to say this is different, okay? And so I'm sure to go back to this. So zero elements are not necessarily corresponding to the trivial extensions. So this is somewhat unexpected though. You look, if you look twice, you say, okay, it's not really surprised. If you lift something, then on the top, you have some value of a trace to come out.
For any semigroup, when you pass to, or even something that's not a semigroup, when you pass to a developing group, there are all kinds of things go crazy. So why is it interesting in this particular setting?
But the extension itself actually is a group.
Which?
All the extension all together is a group. It's just the trivial ones is bad.
Well,
The good you put together, you can add to the still extensions.
I think I find it hard to keep track of which equivalence relations you're talking about.
It's a unitary equivalence.
If you look at all the extensions,
Yeah,
it's unitary equivalence
yeah.
and addition of.
It's like a BDF type of yeah.
Using an O2 containing.
Yeah, so therefore, in particular, you have element which is zero. As a KK element, it's zero, but that one may not be trivial, not correspond to the splitting ones. But
Okay, so you get the extension form a group.
yes,
So, and what is the zero element?
the zero elements are not necessarily
What is the
and-
zero element?
you have because I have you stash isomorphic to, well, I can describe it without saying this. It's just everything is in K0 corresponding to zero elements in the Kroner algebra. These cannot be actually lifted, but you have an element, a zero element in the group.
Okay, what cannot be lifted?
The zero element in the group may not be liftable.
What may not be lifted?
the zero element in the group.
May not be a trivial extension.
That's right. It may not be a trivial extension. Sometimes it is trivial. It depends on the K-theory computation. But sometimes not.
So the zero element in the group is, well, the group, the computation of the group is someone working on K zero.
Yeah, in the W case, you actually has a home of a K0 A to R. So index is a A1 to R. Just this a home. Right. So it's a and there is a one which corresponds to zeros.
Okay, but how do you,
That's not what I mean. This is zero.
K zero?
Yeah.
But how do you get, how do you construct this?
Yeah, construct extensions. Let's say the commutative case, you have lots of projections, each quarter is corresponding to, you add it to R, or you kind of quotient, you go zero elements, zero projection, add together in the Kroner algebra, you can have different values. So you have a continuous function map to the quotient. But everything is zero, but in that particular case, 0, 1 is not good, because otherwise the trace will be zero, and there's nothing there.
So when you have a trivial, so why is it when you have a trivial extension that
So trivial extensions, you want to lift the trace, and which actually can be described. So trivial if only if the KK elements corresponding to the home there. Because you lift it, that is a map to the multiply algebra, so K0 to R. But in particular, the one in
terms of the home,
yeah.
describe the home work with K zero and R, and when is the corresponding extension trivial? There's simple description. I can't read that.
So
Pairing map.
yeah, it's just like a pairing map. That's right. It's just a pairing. Pairing to the multiply algebra.
If it can be realized as the homomorphism induced by a tracial, positive tracial function, then it.
So the home may not be positive, for example. You want certainly positive, right? If it's not positive, it's not liftable. Yeah, 0 is also not good.
That's the only instruction.
That's what it basically says. Yes, there is a scale. There is a scale. So it's you're right. It's a positive, and you also want to say the identity to a thing that will actually lift up. So. And of course, it may not be positive, and these are things certainly cannot be lifted.
That's if you, by trivial, you mean the unit of preserving.
Yeah, and if
Otherwise, it would just be fun.
right, and also there is also better case,
You want values not to be too large.
not too large. Yeah, that's another obstacle, which is probably less important.
Okay, but and this doesn't come up just in the case of the usual extensions, because ideal being the compact operator.
Yeah, that phenomenon usually won't happen there. You have all the stabilizations,
You
and
don't have the same parameterization for the extension.
right, and
There's no trace.
yeah, so we are just looking the KK of A2 Kroner algebra of W.
In this case, the end of the B over B is simple.
Yes, yeah, I want to exclude these cases.
So it's a case of a finite B.
And it's a finite chase, yes.
So then, but even if it's infinite trace, it's still applying to K zero.
And also there's a little subtle things that there is actually corresponding to faithful trace. Even though it's a positive, it may not lift a faithful trace. Because once you have a map from A to the multiple algebra, it gives you a faithful trace. And a home like this, even the positive, it may not be give you a faithful trace. So this is somewhat new to the order.
That's also why you don't want unbounded traces, because you want them to extend to the multiple. You're okay.
So, and then Jamie join us, and we get this is something we already said, I think. And with the get, we have first of all, in this case, we don't really need to assume too much. So A is just separable, amenable C-star algebra. Let me say UCT. I think I forgot to say.
No,
UCT.
you don't need.
You don't need a UCT, right? In this description, you don't need UCT. I'm sorry. That's right. And then this canonical map is in actually isomorphic. So that's why I want to emphasize here is that you do have an isomorphism of this KK element. It's just a different one from the original description. Okay. And we were not completely satisfied with this statement. This is just, let's say, non-unitary unitary equivalence extensions.
It's a strong unitary equivalence.
It's not.
They agree.
This is a weak one. That we have a statement that when they are equal, that means when weak and strong are the same.
It's a non-commutative.
I think the main difference is that well, it's not stable. So that's why addition it is strange. Yeah.
But here, whether it be whether A is commutative or not, it's strong and weak.
Here it's a weak one. This is,
You think it's, I thought you said it was the same.
in many cases, we actually describe when they are the same. And sometimes they are not. There is a K-theory obstacle.
Even when they go to the system.
That's right. There is a K-theory obstacle.
But that only appears for unital extensions. When you're
That's-
working with non-unital extensions, they're always.
When non-unital, because there is a large orthogonal part, you can add a unitary there. So cure the K-theory and you lift it up.
And what happens when you look at the stable idea? For instance, a compact algorithm. In the commutative case.
You mean the in this case, we particularly exclude that case, that we want to have a continuous scale.
Okay, I'm just trying to get some free information.
We actually not completely satisfy this because it's not clear which one's splitting, and we want to say which one's splitting. So let me mention George and Kosarovsky theorem. In the case it's a purely infinite, then there is a good description of the trivial extensions. You have this strong approximate unitary equivalence in the purely infinite simple case. But we also want to see if we have something like that for the trivial extensions. Okay, but in this case there is only one, right? And so I'm afraid I have to say something about the faithful trace and so on. But maybe we don't need to go to these technical details. it's probably annoying. So let's just forget it. Okay. Just to mention there is something little going on, that the trace and not all the trace, only part of a trace actually in the picture. So let me just not to say any of those. I don't think you need to know that either. So here is the theorem. Say if A is not unitary and a extension is livable, if and only if something happens, then we can describe it. It's quite technical, but can be decided. But things are a little complicated. Unitary and non-unitary have to be the different kind of statement. If A is unitary and this element is not the same as unit in the quotient, then tau is livable if only almost the same statement. But if A is unitary and it's already hit the unit in K-theory level, and tau is not unitary, then it's livable if and only if this happens. That we can describe it. They are not the same thing. And then there are examples that is not livable, even though look the K-theory all the same, unfortunately. But maybe we shouldn't say unfortunately, just we know how to do it. It's just complicated to describe, but all can be determined by K-theory. Now, in certain case, we can still describe when it's livable if tau is a unit to A is also unit to. And this part says we know all of those, that given any lambda there, you can find one which hits this element, and it just tells you there are lots of true extensions. So at the moment you thought you know exactly when issue is splitting, but then you look at this Elliott and Voiculescu theorem, as can you have the generalized Voiculescu theorem? But that turns out real hard, because you're really talking about the map from your algebra to the multiple algebra. Okay, say you have two maps, two trivial extensions from C to the multiple algebra, two unit homomorphism. Assume that on the quotient, they are both injective, and they induce the same traces. Then, yes, there exists sequence of unitaries in the multiple algebra, so this works. That is, there are approximate unitary equivalence and difference as in the idea. But it also says that there are lots of them. Not every two of them have this relation. Only those that they induce have the same trace. Now, when we say trace, we really mean that the K0 map has to be the same. They have this strong approximate unitary equivalence. So these are the things I can report today. It's still draft. We hope that it will come out soon. That's it.